Hello everyone, welcome to part 3 of developing advanced RAG. In this video we'll see how we can evaluate the retrieval performance. So what we will do is whatever custom node parser we created in our previous video, we'll evaluate the performance of each of the node parser and we'll see which one is performing better. And to evaluate this retrieval performance we need test cases plus context pairs. So we'll see how we can automatically create 200 plus test case plus context pair using large language model. So let's get started. So in this video we'll use again Llama version 10. So I'm just first installing the packages what is needed. Then I'm just downloading the data, the same PDF file, and then I'm importing all the required packages, and after that I'm loading the data and creating documents out of it, which I'm storing in the docs list. And then what I'm doing is I'm loading the large language model. So I'm loading from HuggingFaceLLM and doing contortion. So this is my Zephyr 7B alpha model, and these are set of parameters which I've already explained in my previous video. So once my model get downloaded, then what I do is I'm downloading the embedding model, which is BG base embedding, and I'm storing into settings.embed model. Next, I'm calling SentenceSplitter with a size of 1024. So I'm creating all my docs into different chunks of size 1024 and storing as base nodes. And now these base nodes will be treated as a parent node for all different parsers, and that's why I'm converting their IDs into a fixed number like constant node 0, node 1, so that I can do a lookup file evaluating them. So next I'm just importing our different custom parsers what we created, like ParentToChildrenNodeParser, which I explained in my previous video only, ParentToSentenceNodeParser, so that we can evaluate it. So next is the evaluation piece. So first we'll see how we can evaluate, like how we can generate the dataset which we need for evaluation. So from LlamaIndex.code.evaluation we will import this function which generate quotient to context pair. So what it will do is for every in this quotient to context pair we pass all the base nodes, the LLM model, and we say okay, for every chunk give me 5 different questions, and it will generate using LLM 5 different questions for every chunk. So we will have around 200 plus different question to chunk pair, and then it creates a mapping also, like this question was generated from this chunk, so that chunk becomes the main reference chunk. And then while testing the different retrieval pipeline like the node parser, we'll see for a given query did we get the reference chunk or not. So it will take time to generate these questions. So what I've done, I've just saved it also, and I will just upload these question of context pair as JSON into my GitHub, so that if you don't want to run this cell, you can just load it directly from here. I'm just loading it from Kaggle, so I've given Kaggle path. Just change this path as per your location wherever you are saving this JSON file. So if you see, I got queries are the questions, 201 questions I got, and the length is of base nodes was 38. And this is how it creates a query and doc ID pair. So query is the question, doc ID is the base node or the node from which this question got generated. So this node becomes a reference node, and while asking the retriever this question, if I get this node, then if I get this node in top 3, and I set a KS3, and if I get this node in top 3, then my hit rate would be 1. If I get this node at the first position in top 3, then my MRR would be 1. So basically hit rate is it's a binary score which says your correct chunk is retrieved or not. So if you are setting K as top 3, and if you are retrieving top 3 chunks, and if your current chunk is present there, then you will get a score of 1. Where MRR, which is mean reciprocal ranking, which evaluates the position of the chunk. So in top 3, at what position the correct chunk is there. So this is the formula. So 1 divided by rank I, where I is the index where you got the chunk. So if it's at the first position, the rank I would be 1, so 1 divided by 1. If your correct chunk is at the second position, so it will be 1 divided by 2, you'll get a score of 0.5. And similarly, it's third position, the 1 divided by 3. So both the metrics, higher the score, it's the better. So hit rate is 0 to 1. MRR also is 0 to 1, you get it. So let's set up the pipeline. So we are setting top K as 3. So we want to retrieve for every question top 3 chunks. And this is the helper function, like display results to display the final result, which we'll use later. So first I am evaluating base retriever evaluation. So what I'm doing, I'm just passing all my base node which we created earlier into VectorStoreIndex, and I'm just saying like calling vector index base index as my retriever with top case 3 as my base retriever, and then just passing into this retriever evaluator function this base retriever and the matrix like what we want. And once you run this, you will get it, like it will evaluate this retriever on the complete question context pair and give you the result in this results underscore base data frame. So this is 200 questions it evaluated. Second, we'll do the same thing for parent to child node parser. So I'm calling parent to child node parser. 1024 is my parent chunk, 512 and 256 is my child chunks. And then I'm just getting all the child nodes and the parent node mapping. Then I'm passing to VectorStoreIndex, then I'm calling it as a retriever with top k as 3, and then I'm passing it to RecursiveRetriever where and this vector retriever dict is where I'm passing this retriever. I'm creating an instance of it which I'm passing to retriever evaluator, and the same thing, it will evaluate and it will store the results into results underscore chunk underscore p2c. Same thing I will do for parent to sentence node parser. So again, I'm passing a chunk of 1024, so it will, for every chunk it will create different sentences and will do the mapping. So I will get all the sentences here, all the mapping here, pass it to vector source index, then call it as a retriever, pass this into your recursive retriever, like this one is passed here, and then this is passed to your retriever evaluator pipeline, and you get the final results at results underscore chunk underscore sentence. So let's see the performance. So we'll see what is the hit rate and MRR we got when we set top KS3. So this is my, I'm just passing all the metrics and with the column names into this function, helper function, to get the final DF, and this displaying the final DF. So if you see, it's for the base retriever, my hit rate was like 0.91, but my MRR was very low, like it's like what 81, like around 82% only. And for my first retriever, which is parent to child node parser, I got hit rate of 93% and MRR drastically improved to around 88%. Then parent to sentence node parser, where I'm doing a query at a sentence chunk, I'm getting a hit rate of around 97.5% and MRR around 93%. So this shows the best one is parent to sentence node parser. So just search the chunk, like create chunks of sentences, and while querying just search at the sentence level, and whatever sentence you found, just get the parent node out of it using the mapping what we created. So, and it works pretty well. It will always give you like 97.5% cases you get the correct chunk in top 3. So in, I think the performance what we get is pretty good with this basic retriever system, where just I'm focusing more on the chunking strategy, not using any fancy stuff of like re-rankers or rag fusion or the different advanced techniques. So next we'll see, can we improve it further? Like, can we at least get a hit rate of 100%? I think that would be a dream kind of situation. So we'll see in next video how we can achieve a hit rate of 100% and MRR pretty close to 100%, and by just following the same different chunking strategy only. So thank you for watching this video. Please share your feedback in the comments and do like my video and subscribe my channel. Thank you.